Now I'm going to talk about the Nelder-Mead Downhill Simplex Method. This is a kind of numerical method. That means we are going to do iteratively to find a local minimum. So this Nelder-Mead method, that is a kind of local minimum search algorithm, for several variables. It means that it is possible for us to deal with a cost function with multiple variables. But in this example, or in this method, I only introduce a two-dimensional case. It means that we only consider two variables with x1, x2. So when we talk about a simplex method, simplex, it means that it is a kind of geometrical figure, that is an object formed in n-dimensional space. That is, if we talk about the n dimension, two variables, we will have 2 plus 1. That is a two simplex, that is a triangle. Later on, you will just find out that we are going to use a triangle to roll the triangle in the landscape of the cost function, so that to find the local minimum. And when we talk about a three simplex, and then that is a tetrahedron, so and so, And so you can just find out that. So I have a video clip right here which can demonstrate how actually this simplex method worked. Okay, just take a look at this video. And okay, so we have this object with 4 legs, and then if we are going to stick it into the raw, and then you will just find out that there would be one leg that is going to the downward, that is to take the highest point to the lowest point due to the gravity. So we are going to do the same in the simplex method. That is, we are going to create an object something like that. Okay, sorry. So in a simplex method, we have something similar, that is an object with a number of legs, and then so when we, as I mentioned, about two simplex, that is a triangle, you can imagine that we have a 3 legs object that is rolling down the landscape. So the goal is we are going to search the local minimum. Again, this is the minimum seeking algorithm. That means we can only find the local minimum when we talk about minimization problem. And then the step is that first we are going to move the simplex toward the local minimum. We call this is the refraction and expansion. I'm going to talk about this later on. Through the rolling of this triangle, and then so we are going to surround the minimum. Once we surround the minimum, we are going to reduce the size of the triangle, so that we are going to get all the legs or get all the corners closer to the local minimum. We call this is the contraction or the shrinking movement. So we are going to repeat this process. That means each time we are going to pick one of this action and then to repeat this process until we find the local minimum. So in general, we have 4 kinds of movement: refraction, expansion, contraction, and shrinking. Now I'm going to show you another animation, so that I'm going to show you all these 4 kinds of movement, and then how do we locate the local minimum. Now right here, assume that this is a landscape. That means when we find out that the blue space right here, they are the function of x. So because this is a two-dimensional space, for example, this is x1, this is x2, and actually when you talk about the height, so we have the height, that is f, that is x1, x2. So a two simplex, that is a angle, that is a triangle. So now what we are going to do is, first we are going to construct a triangle that is a two simplex, and then we have 3 points. It is something like an object with 3 legs. So now what we are going to do is just to do the refraction. We have a triangle, something like that. When we evaluate the cost of each point, we just find out that this point is the highest point. So what we are going to do is just to roll this triangle along this side, and then bring this vertex to the lower point. So what we are going to do, that is something like locate the highest point and then create another triangle. Flip this triangle so that this point becomes this point. We expect that this point is lower than this point. That is something like what we have done in the four-legs man in the previous video clip. Okay, now we have done one iteration. We are going to rotate this triangle, flip this triangle into this one. Now we have improved the solution. That is, when we look at these three vertices, and then this vertex, it has improved its performance. So that is about the rolling. That is about to flip the triangle, move the triangle toward the local minimum. For example, right here, the local minimum, that is right here. So we are going to repeat this process. Flip this triangle into this region. Yeah. Okay. So the next step, that is bring this triangle, the highest point to the lowest point, and then this is about the refraction, or we call this. We have two actions about moving toward the local minimum, refraction or expansion. I'm going to explain this later on. Now we have another action that would be, look that this yellow triangle, that is not this one, because we expect that we flip this triangle, at some point it becomes this yellow triangle. This yellow triangle, that is very close to the local minimum right here. So no matter where this triangle is going to flip, it does not give you better solution. Yeah, because when you flip to this triangle, for example, the lowest point, that is right here. Yeah, so we cannot improve the search anymore. In that case, what we are going to do is just to do the contraction, reduce the size of the triangle so that the triangle become closer to the local minimum. And now take a look at this one. The original triangle, this is the original yellow triangle. We bring this point to the center. Okay, actually something inside, not exactly the center, and then now the triangle becomes smaller, and then so this is a kind of contraction, reduce the size of triangle, so that we are going to improve the cost of this point. So now the next movement, we call this is shrinking, so that we are going to do something right here, and then we may have a triangle in this scenario. Again, this green triangle, that is not this one, not this one, and then so in each iteration, we only have one triangle in this space. That means when we roll this triangle during the contraction, at some point it becomes this green triangle. And now the same case, no matter where you flipped, we cannot improve the cost. Yeah. So what we are going to do, that is to bring these 2 points closer to the best solution, because we are talking about minimization. So this is another option for us to reduce the size of the triangle so that it brings the triangle, all the vertices, closer to the local minimum. Yeah. Okay. So this is the fourth movement I just showed you. Okay, later on we are going to bring these four kind of movements together so that to form a kind of algorithm for us to start from any point in this landscape, find the local minimum. Yeah. Okay. Now we are going to see all these kind of movement in action, in a sequence of action, in this animation. Yeah. So this is what we can see. We have the initial triangle right here, and then so we are going to flip this point into this one, so that we are getting closer to the local minimum. This figure, the x-axis, that is the first variable x, the y-axis, that is the another variable y, and then so we are assume that we are going to look at this landscape from the pan view, the top view. So these lines indicate the level, how the cost in this circle, they are the same. For example, this level that is 5, this level that is 6, so and so. Yeah, so each line will have a value that is due to this cost function. Yeah, so the local minimum, we assume that that is somewhere around here according to the function we have in this example. So the next step, that is, we're going to do similar thing, flip the triangle, and then now this is a kind of the movement we have mentioned before, refraction and or extension. The purpose, that is to roll or to flip the triangle, moving it toward the local minimum. Yeah, because at the moment we still cannot locate the local minimum. So what we are going to do, that is to keep doing this action. Okay, so you can just see that we are going to do something like that. You will find out that now this is we locate the local minimum, and then so after we flip the triangle, and then now you will just find out that this triangle is not the same as this triangle in terms of size. That means we have, instead of doing refraction or expansion, we have done the contraction or the shrinking. Yeah, so the triangle becomes smaller and smaller, and so that we come up with something like that. Reduce the size of the triangle so that we are going to refine the solution so that we are able to find the local minimum. Yeah, so that is the thing we are going to do. Okay, take a look at this figure, and this slide just shows the first step. And in order to implement this algorithm, first we need to create a triangle. A triangle, that is, we are given 3 points. These 3 points, that is x1, y1, the first point, x2, y2, x3, y3. That means in a landscape. And then so what we can do is, we have a curve right here. We can just simply pick 3 points, and then so this is x1, y1, and then this is x2, y2, this is x3, y3. And now, after we have these 3 points, and then we have to evaluate their cost. For example, when we are given a function that is with 2 variables, x and y, the function that is x plus y, say when x, that is 2, y, that is 3, what we are going to do is just to plug it into this function. We will just find out that the cost, that is 5. So we are going to evaluate all these x, y value, and then label them and assign b, g, w to these 3 vertices according to this condition. That means for the best vertex, that means its cost, that is the smallest among these 3 points. Yeah, so that is because we are doing the minimizations, so we are calling this the best cost, the best vertex, that is b. And then the worst one, that is the one give you the largest cost, we are going to assign that to be w. Yeah, and then the middle one, that is g. So it satisfies this condition in some special cases, and then if they are all the same, and then we can just simply randomly assign the label to them. But in that case, because all the points they are the same, if that is the initial, if this is the initial iteration, we are going to choose another 3 points. Otherwise, if we are going to have this case happen in the algorithm, that means we already find the local minimum. Yeah, so now, as I mentioned before, the triangle, initial triangle, that is, we are going to do the flipping. Yeah, move this point to this point. So this is the flipping of this triangle. So when you look at the dark gray triangle, that is the initial triangle, we have 3 points b, g, and w. It means that after the evaluation, we already locate these 3 points. The light gray triangle, that is after the flipping, and then after the flipping, we call this is the action of refraction. So we flip this point to this point, so this point, we call this is R. Yeah, so we flipped along the BG side. The flipping, that is, what we are going to do, that is to find the midpoint right here. And then according to the midpoint, we find the distance. And then so we are going to flip this triangle to the same distance, D. We can find R, yeah? Okay, let's see what the equation about this, yeah? This is the minimization problem, two variables, the cost function, that is fxy, the midpoint, that is, because the midpoint must lie in BG side, yeah? So the midpoint, that is B plus G divided by 2. So assume that this is x1, y1, the G point, that is x2, y2, the midpoint, that would be x1 plus x2, yeah? x1 plus x2 divided by 2. The y coordinate, that is y1 plus y2 divided by 2. So this is the midpoint. So once we find the midpoint, what we are going to do is, if we are going to find the refraction point, that is in the opposite direction of W and with the same distance D. So M, this point, minus W, and then this is the distance or the vector, that is D, yeah, that is the distance D, and then M plus this D, which give you R. So M plus M, 2M minus W, that is the equation for R. And then so now we have another refraction, another version of refraction. We call this is the expansion. The difference is that instead of moving 1D, we are going to do 2D. It is because that in some cases, if we find this is a good direction to search, yeah. Now, when we search, we find that this direction, this is the worst point. The opposite direction, it could be, or it may be, a good search direction, yeah. We cannot have a proof for that, but we assume that in the opposite way, we are able to find a good direction for search. If it is not the case, we are going to use another move in the algorithm. Assume that when we flipped the direction in the R, we find that R is a good point, is a very good direction. Why not we extend this search distance from D to 2D? That is the expansion. So that's why we are going to have 2D. Of course, we can extend this to 3D, 4D, yeah, but we do not do this, yeah, because we are going to repeat this process iteratively. So in this algorithm, we only do 2D, yeah. So the expansion point right here, that is, if we are going to find R, we already have the R, and then R plus R minus M, that is this distance. Actually, this is the same as this distance. So we just simply add R minus M, that is D again. So we have 2R minus M, that is this point, yeah? Okay. Now I have defined the refraction and expansion. So this is these two actions or two movements, mainly to roll the triangle toward the local minimum. When we are at the local minimum or surrounding the local minimum, and then the refraction doesn't work, yeah? So what we are going to do is just to do contraction or the shrinking. Now this is the contraction. This diagram just shows the contraction. We handle the same minimization problem and then the contraction point, that is C. So that means once we have this triangle BGW in the current iteration, no matter what you are going to roll, refraction, expansion, you cannot find a good solution. That means most likely a better solution should be inside this triangle. For example, this point, okay? And then now what we are going to do is just to bring the worst case, the worst vertex toward or inside this triangle to form this triangle, yeah? So bring W to C1. Or we have another option, because no matter what you are doing, you cannot improve the solution. So we are going to reduce the size of the triangle So instead of doing C1, we can use C2. That means this large triangle become this one. Which one is better? We do not know. Yeah. So that means we only provide two options right here. Either bring W to C1 or W to C2. If you are going to use C1, this is the equation. W plus M, that is the midpoint, that is C1, so divided by 2. C2, that is the midpoint of R plus M divided by 2. Yeah, so we have this equation, the C2. Yeah, later on, I'm going to demonstrate integrate C1, C2 in an algorithm. Yeah, the next one, the shrinking, and then the idea, that is the same. So no matter what you do using expansion, refraction, or contraction, it does not give you a better solution. And then so that means what we can do, that is to shrink toward B. B, that is the best solution. The best solution, it means that the cost function is the minimum among these 3 points. So when we have nothing to do, when we cannot do nothing to improve the performance, it indicates that what I mean that is what we can do is just to bring the worst point toward B, bring toward the G point toward B, so that to reduce the triangle. Yeah, so this solution will be closer to the best solution. We expect that this S as well as the point M, they can improve the performance compared with W and G respectively. Yeah, so S, that is the midpoint between B and W. So B plus W divided by 2. M point, B, G, the midpoint. So B plus G divided by 2. Yeah? Okay. Now, just a quick summary. We have 4 movement. Refraction, flip the triangle with 1 unit of distance in the opposite way of W. And expansion, that is flip the triangle with 2 units of D in the opposite way of W. And then the contraction, that is reduce the triangle by bringing the worst vertex into closer to, bring it inside the triangle or in the opposite way. Shrinking, that is bring the W and G toward the best point. Yeah. So we have these 4 movements. And now we have the flowchart as well as the algorithm to tell you how do we combine all these things together. Okay, so this flowchart, that is just to put all the refraction, all the 4 movements together to form an algorithm. Yeah, so we have the refraction, expansion, contraction, and shrinking. I'm going to talk about this flowchart later on using an example. But anyway, we are going to talk about this algorithm. This algorithm, that is the same as this flowchart. Yeah, so the procedure is the same as this flowchart, but it is in the form of the pseudocode. Yeah, so now this algorithm, Nelder-Mead Downhill Simplex Method, that is for a 2-dimensional case. It means that we are going to have 2 variables. Say we have a function that is x1, x2. Maybe we are going to use x and y. Yeah, x and y. So in a 3-dimensional space, we will have something like this: x and y, the z-axis, that is the f. Okay, x, y. Okay. In that case, this is a 2-dimensional case. When we talk about 2-dimensional case, it means that we have 2 variables, x, y, and we have a cost function f. And then so now we are going to look into details. How do we apply this algorithm, making use of the 4 movement: refraction, expansion, contraction, and shrinking? And now, if this is the first iteration, what we are going to do is just to randomly pick some vertices, 3 points. For example, right here, form a triangle, and for each point, we are going to evaluate its cost by putting this xy value into this cost function, and then we are going to pick the one which gives you the minimum value, and then that is the B. Yeah, because we are talking about minimization, so we are looking for the minimum cost. And then another point, that is the good point, the worst point. The worst point give you the largest cost among these 3 points. Now, when we first enter this algorithm, what we are going to do, that is to check whether the R point, the cost, that is less than the good point cost or not. Yeah. So that means we are going to do refraction in the beginning. And then this is the R point. We are going to evaluate whether this R point better than good point or not. When I say better, because this is the minimization problem, so the cost of R should be less than the good point. Okay, if this happens, we are going to do refraction or extension or expansion. Yeah, so this is this process, and then otherwise we are going to do case 2, either doing contraction or the shrinking. That is this column. Okay, and now when we find out that the refraction point, that is less than the cost, less than the good point, it means that this solution is above average. Yeah, so it means that at least we are searching in the right direction. Yeah, so this is a good direction because it is better than the good point. So we are going to do case 1. The case 1, first we are going to check whether the refraction point larger than the best point, that is the cost of R larger than B or not. If it is larger than the best point, it means that although the refraction point, that is better than average, but it is not better than the best point, that is it is okay but not good enough. We are searching in the right direction. So I said, yeah, so it is not necessary to extend this refraction point to the expansion point. Yeah, so that means we only search 1 unit of distance and then we stop this iteration. So what we are going to do is just to replace the worst point W by R. Yeah, so that means we are going to disregard this dark triangle and then we form a new triangle BGR, and then this is the end of this iteration. Note that this is just 1 iteration. We are going back to the top of this algorithm and repeat this process. Now we have BGR and then we have to do the relabeling and then evaluate all these costs and we assign this label to BGW. Yeah. So after we relabel, for example, that would be because when we enter this step, the R point, that is lower than the G point, but not better than the best point. So one logical thinking, that is the B point still the B point, the R point will become the good point, this one will become the worst point. Okay, so when we get to the top of this line, and then we are going to find the refraction point again. That is because this is the worst point, and then we are going to form a triangle right here. That is the new refraction point, and do the same. If the refraction point, that is less than f of g, assume that it is the case, we are going to case 1 again. But now I assume that if fb, that is not less than fr, that is fr, that is less than b, we are going to into the else block. Yeah, so that means in that case, because the refraction point, that is even better than the best point, and then we are going to do this, and then it indicate that we search in a very well direction. Yeah, so what we are going to do is just to compute the E point and then find its cost, and we are going to check this thing. If the FE point, that is less than the best point, yeah, the E point that is less than best point, this is a minimization problem. It means that we find some good solution. So what we are going to do is just to replace W with E. That means this W. Now this triangle, that is this triangle in the previous iteration. So what we are going to do is just simply replace W by E. So now we are going to remove the dark gray triangle. We use the light gray triangle, yeah, in the next step. When we get to this point, that is the end of this step. But if it is not better than FE, that is not better than FB, we are going to do this step. That means now it is in a good direction, but once we find out that the expansion point, that is not less than the best point, it seems that this direction, although it is good, but it may not be good enough. So we are going back to the refraction point. So we are going to replace this W by R. So this one becomes W. Of course, at the end of this iteration, we are going to relabel this BGW point, yeah, according to their cost. So this is the case 1. And now, in case 1, this step, we end with refraction. In this step, we end with expansion because we replace W by E. In this step, we end with refraction. And now, what about this case is not satisfied? That means R that is larger than the cost of G. It means that this is not a good search direction. Now, it indicates that maybe we already flipped the triangle to the local minimum. Now we are surrounding the local minimum. So we are going to do contraction or the shrinking. Yeah. So in case 2, when we first enter case 2, we are going to do some refinement. That is, we are going to still find the refraction point according to the BGW point, and then we are going to check whether this refraction point less than the cost, less than W. That is, whether this point is better than this one. If it is, and then we are going to disregard this triangle and then replace that by W. Yeah. Okay. So this is just a refinement. So after this point, when we talk about W, that is this new W point, that is the R point. Okay, so this is something very important we have to take note. Note that after we get to this point, we do not need to relabel this BGW because according to this logic, this R point that is larger than the good point. That means this point, the cost, will not be better than G and B. Yeah, so it is just better than W. So when we replace W by R, and then we still have this order B, G, W. Yeah, so right here we are going to start with the new W, that is R. Yeah, and now when we get to this point, we are going to determine whether we are going to do contraction or the shrinking. Now, if we are going to do contraction, we need to find C1 or C2 in order to replace W by C1 or C2. So we have 2 options. The first one, that would be this equation. Another one, that would be this equation. There are a number of options to do this. Either each iteration randomly pick one, randomly pick one of the C, or we are going to fix one of this expression throughout all the iteration, or we are going to compute both of them and pick the one with the better cost. But anyway, assume that at the moment we have the C point and FC point ready. Yeah. Okay. Now, when we enter this step, we are going to compute the cost of C. We are going to check whether this C point less than W. Yeah. So that, for example, I'm going to pick this to be C, and then so whether we are going to check whether this cost is lower than this one. If it is, that means at least we find one point that is better than W. So now what we are going to do is just to replace this W and then so by C. So we have these 3 points, and then that would be the end of this iteration, and we end this algorithm. We end this iteration with contraction, and then we label the BGC point in BGW point and go back to the top. Repeat this process. Okay. And what about if this condition is not satisfied? It means that the cost of C point that is larger than W. Yeah. So that means when we find out that after all these actions, we cannot find any point better than the worst point, what we are going to do is just the last resort. We are going to compute S and then shrink, replace W by S and replace G by M. So that means we are going to shrink W and G toward the best point. That is the last resort, because at the moment we cannot find any best point. So we believe that if we are going to move all other vertex toward the best point position, and then so we can improve the solution, because that is the only step we can do. Yeah. Now, how come right here we do not need to find out the midpoint? It is mainly because when we find the refraction point, we need to have the information of the midpoint. Yeah. So that's why we already have the midpoint information. Yeah. So that means anyway, now we have all the information right here, B, S, as well as the M point. That is, we exit this iteration by shrinking and then go to the next iteration. We have to relabel this B, S, as well as M into B, G, W. Yeah. Okay. Repeat this process until we believe that the solution is good enough, and then so we can stop. Yeah, that is the stopping criterion. We can talk about this later on through an example. Okay, now this is question 4. That is about the minimization of this function, 2 variables as well. Again, for this algorithm in this pseudocode, we can only use that to deal with a 2-dimensional cost function. That is, we only have 2 decision variables. If we are going to extend it into a higher dimensional space, we will use another version. Yeah. So could everyone spend 5 minutes to look at this question and then to think about that whether you are able to apply this method or not? And then so during attempting this question, if you have any issue, just let me know. Yeah. So shall we look at this question by 5 minutes? Yeah, so if you have questions, just ask. Yeah, because I also see that there are some questions in the chat.
Yes. Hello.
Yeah.
Yeah. So yeah, I've understood the reflection and expansion. Can you briefly, just so you save me some time? I mean, I'm sure that we can all follow when we read along, but when you go to from the T5 to T6, when is this construction? Can you briefly explain the same way that you did in the lectures, why we construct and why we don't reflect eventually?
Yeah. So in question 4 in the tutorial, and then we are going to use another bunch, and then you will see why we are going to contract or shrinking. Yeah. The main idea is that if you look at T5 and then T6, you will just find out that if you're going to do refraction in the opposite way, the cost doesn't improve. That is, the case 1 and case 2. That is mainly about case 1 and case 2. So try question 4, and then I'm going to come back to your question.
Okay, thank you.
Okay, so I hope that everyone has found time to understand about what this question is asking, and then I'm going to go through the details about how do we apply this method. Yeah, so in the chat there are some questions asking, and then someone asked that when we should stop. So that is, we can set up our criterion, that is after many time of iterations, if the 3 points BGW does not change for a certain amount, and then we can stop. So I think that you can just determine your stopping criterion for yourself. And then the second question, that is about the shrinking and the contraction. And then in this question 4, I'm going to illustrate why we do not do the refraction instead. And then another question, we supposed to complete this tutorial question in our own time. So I think I would suggest that everyone try the question at home first, and then doing the tutorial, and then I will go through the details so that we can the first one, that is you get the idea what you're doing, and then as well as what you have done watching the video, and then during the tutorial I will go through further details and try to answer the question you have. Okay, so of course if you do not do it in your own time, and then it is absolutely fine, because I understand that everyone is busy. So I do not so I will leave this to you to determine how do you manage your time. Anyway, for question 4, this is question 4, and then we try to understand what this question is asking. So we're going to apply this downhill simplex method to this two-dimensional cost function x and y, and then this is the cost values we have in reality, and then no one will give you the cost function. We have to find this cost function according to the applications. And then this question, that is, we start with these 3 vertices. So again, these 3 vertices, I just randomly pick them. Usually they are confined in a small region. Okay, so if you're going to choose a very large triangle, and then actually this algorithm works as well. But anyway, I just randomly pick these 3 vertices, and then we are going to find M and R, and then determine the 3 vertices in the next iteration. So this is what the question asked. So according to this information, we have 3 points. 1, 2, 3. So we have to determine which one is the best point, which one is the good point, which one is the worst point. So what we need to do is just to plug in these 3 points into this cost function. The one give you the smallest cost, and then that would be the B point. And then the same for the worst point, the one with the largest cost. Yeah, okay, because we do minimization, and then the one in the middle, that is the good point. Okay, now just see what we are doing. So according to the finding I have, this one substitute the first point into this function, it gives you 0 the cost. So, and then the same for the 2 points. So according to the cost, this one will be the best point, this one will be the good point, this one will be the worst point. So I put it in this figure. Based on this information, I apply this equation, and then I'm able to find the midpoint. So up to now, I hope that everyone can follow. Yeah, if you cannot follow, just let me know. So we have the BGW and then find the endpoint. Based on the endpoint, we are going to find the refraction point. So this is the diagram we have. So now we have the initial point, we have evaluate all the starting point. Now we have the BGW. At the moment, we are at this box. This box, that is, we determine whether we are going to do refraction or expansion, or case 2 contraction or shrinking. Yeah. And now we are going to check about this value. Based on this formula, we are able to find that this is the refraction point. Okay. The refraction point, the cost, that is 8. Now we are going to compare. This is 8. The good point right here, this is the good point 6. Okay, so this is what we are doing now. So 8, that is not smaller than 6. That means we are going to go to this branch. So that is the previous question just asked why we are going to do, when we are going to do refraction expansion, or when we are going to do contraction or shrinking. And now the rationale behind is that now the refraction point, that means we are going to do the triangle refract to here. But we just find out that the refraction point, that is not better than the average, that is the good point. It indicates that the refraction is not very useful. We are not searching in a good direction. That means this direction, it is not a good direction. So we are going, it implies that the optimal point would not be in this direction, but maybe somewhere in the middle. Yeah, somewhere in the middle. So we are going to do the contraction or the shrinking. This is the rationale. We believe that it will happen. Yeah, so there's no guarantee, but we just try. Yeah, okay. So we go to this direction, and then so now we are at this block to make the decision. Now we have the R point, the cost, that is 8, and then so we have the worst point. This is B, this is G, this is W, and then W, that is 26. 8, it is smaller than the worst point. It seems that we are doing good. At least we are doing good because we are able to find a point that is better than the worst point. So we go to this direction, yeah, because the answer to this question, that is yes. Now we are at this point. We are going to replace W with R. Remember that once we get to this point, the original W point will be the point R. Yeah, so that means from this point on, we are going to use R to replace W. That means from this point on, when we mention about W, that is R. Yeah. Okay. So up to now, we are able to improve a little bit. That means the worst point is replaced by R. Yeah. And now we are going to go to this box. This box, that is, we are going to compute C. The C value, that is, if you refer to the previous slide, and then the C point, that would be upon either this C1 or C2. we are going to choose one of them. Yeah. So according to the previous question, we use this C point. Yeah. Okay. Now, why we are going to use this C point? Because I'm going to make the question checkable, so that I just specify that we are going to use this point as C. Yeah. Anyway, we are now here. We compute C using the worst point as well as the W point. Again, the worst point now, that is the point R right here. Okay, now we call this is W. So we can compute that the C, the cost, that is 1.06. Now, after we do this compute C, and then so we are going to go to this block. This block, we are going to check whether the cost of C less than W. Now, the C point, that is 1.06 W, that is 8, because now the W point, that is this R point. Yeah. Okay. So 1.6, that is less than 8. So the answer is yes. So we are going to do the contraction. Yeah. So we stop at this point, at these blocks, and then this action, that is contraction, because we are going to make the triangle smaller, not doing refraction, because potentially when we go to case 2, it means that the solution is very close. Maybe we are going to do expansion refraction. We will skip the optimal. So we are going to make the triangle smaller so that these vertices will become closer to the optimal point. Yeah. Okay. So we end up with this point. We replace the W with the C. So we come up with 3 points, B, G, as well as C, in order to go back to the top. And one another iteration, we are going to relabel this 3 point. Yeah, BGW, because this point, that is smaller than that is larger than B but smaller than G. So in the next iteration, this point will remain to the best point. This one will become the good point. This one will become the worst point. Yeah. Okay. So is that all right? Okay. So do you have any question you would like to ask?
Professor, and in the slide page 36, and the contraction point C have C1 and C2. And
Yep.
what is the difference between this C1 and C2, and how should we choose the contraction point C between these 2 points?
No, we do not have any idea which point we are going to use. That means either we are going to randomly pick C1 or C2, or you are going to calculate 2 points, C1 and C2, pick the one with the smallest cost. Because why we come up with C1 and C2? Because at that stage, we want to make the triangle smaller so that these 3 points will come closer to the optimal point. But we do not know which point C1 or C2 is better. We just randomly guessed that that would be either in the opposite direction of the existing triangle or inside the body of the existing triangle. Yeah, so that is just some options we are going to use.
Okay, that makes sense. Thank you.
Okay, so let me just check that whether we are good. Yeah, there's some questions right here. Why we check contraction before? Why we check contraction before shrinking, or they can swap? So you do, is that your question? You just ask C1 or C2? Okay. So yeah. So if you can give me a little bit more explanation, and then so I can answer this question. And then next question, that is to design, we need to contract or shrink. We need to iterate case 1 at the first iteration every time to find out. Yes, that means when we apply this algorithm, in each at the start of each iteration, we are going to check whether case 1 or case 2 we are going to go. Yeah, so this is what we need to do based on every new triangle, the 3 vertices. Yeah, okay. So the next question, it seems that in this question C is the midpoint of R and M. Why C? Okay, no worries about whether this C point is coincident with M or not. We just follow the procedure to find out the C point. C point is the C point. Use the equation we provide in the slide. Yeah, sometimes there may be some coincidence that it is the same as some other points. Yeah, so the final W should be okay. Let me just the final W should be 0.75. Yes, if you are looking at this one, if you are going to look at this step, W, that is C. But what I'm talking about that when we go back to the top of this flowchart, we have to relabel the BGW. So the C point originally that was W, but before we start this procedure, and then so we have to relabel, and then C point will become the good point. Yeah.
So the calculation for C has a M variable in it, but since we replaced the R with a W in the last iteration, does that mean we need to recalculate M to find C every time we do the swap?
Okay, yeah. So that means no matter what, we need to find the M point first, because right here, I'm going to circle these blocks because we need to use the R point to determine which way we are going to go. So refraction point depends on the M point. So no matter what, we need to have the M point ready. Yeah, so I get what you mean. The M point. Okay, so the M point that is calculated according to this equation. Yeah, according to this equation, please refer to the slide. Using the BG point, we calculate the M point. Yeah. So is that all right?
Yeah, thank you. So basically, we always recalculate M when necessary.
No, we do not need to recalculate M. That means M we already calculated at the beginning of this algorithm. That is right here. Yeah. So that is to determine whether we are going to use case 1 or case 2. We already calculate the M point.
Okay, so is that because after a reflection, the endpoint stays the same, right?
Yeah, the endpoint stayed the same because the BG point will not change. Yeah, so we do not need to calculate that.
Okay, thank you. So
Okay.
we only recalculate when there's a change in B or G. Basically.
Yeah, exactly. That means when we go back to the top of this algorithm, we need to BGW point will change, and then in that case we are going to calculate the endpoint as well as the refraction point.